Hey everyone. So, in the big race to make AI faster, we usually think bigger is better, right? More power, more processors. But what if the biggest slowdown wasn't caused by the big stuff at all, but by one of the absolute smallest calculations? Today, we're going to uncover a hidden traffic jam happening inside the world's most powerful AI chips and the really clever engineering that fixed it. Let's dive in. So let's start with this. We all imagine making AI faster is about just throwing more and more raw power at these massive computations. But what if the real problem, the real speed bump, was hiding in plain sight, in one of the tiniest, most complex parts of the entire process? To really get our heads around this hidden bottleneck, we first need to understand a really fundamental concept that makes modern AI even possible. We have to look at how these models actually, how they pay attention. At the very heart of models like ChatGPT is something called the attention mechanism. And honestly, it's pretty much what it sounds like. It's a system that lets the AI figure out the importance of different words or pieces of data. It's how the model knows that the word bank means a place for money in one sentence and the side of a river in another. It's all about creating context. So how does this actually work? Well, imagine every word, or what we call a token, is having a little conversation. Each one plays three different parts. First, it sends out a query, which is basically asking, hey, what other words around here can help define me? At the same time, other tokens are holding up a key, saying, this is the kind of context I've got. And when a query and a key find a good match, that token then provides its value, the actual information that helps build the final meaning. So, after all that, the model has this big jumble of raw relevant scores. To make any sense of them, it uses a clever little math trick called the softmax function. You can think of it as the final judge. It takes all those scores, turns them into a nice, clean set of probabilities that all add up to 100%, and tells the model exactly where to focus. It's an absolutely critical step. But, and this is a big but, it's also the source of our hidden speed bump. Which brings us right to our next section, the GPU traffic jam. Because as it turns out, that critical softmax step was causing a major slowdown right in the heart of the processor. Now, to really see the problem, you gotta understand how a modern GPU is built. You've basically got two very different parts working together. On one hand, you have the tensor cores. Think of this as a massive multi-lane superhighway built for billions of simple calculations, like addition and multiplication all at once. But then, on the other hand, you have the special function units, or SFUs. And these are more like a narrow single-lane bridge designed for much trickier transcendental math, things like the exponentials you need for that softmax step. And right here, this is the whole problem. That entire superhighway of tensor cores has to come to a screeching halt and just wait in line for that single-lane bridge of SFUs to finish its complex work. This softmax calculation creates what's called a pipeline stall. It's a traffic jam where your most powerful, most expensive processors are just sitting there, completely idle. And this diagram, this shows you exactly what that traffic jam looks like. The process starts, the tensor cores are just flying, calculating all those initial scores. But then, bam, everything just hits a wall. The SFUs have to take over for the softmax step, and just look at that big red idle block. That is your multi-billion-dollar superhighway sitting empty, cars parked, just waiting for one little bridge to clear. All that processing power totally wasted. But NVIDIA saw this traffic jam and they designed a really clever solution for it in a new version of their chip. So let's move on and see how the Blackwell Ultra clears the road. The solution is actually beautiful in its simplicity. I mean, if the problem is a single-lane bridge causing a backup, what do? You make it a two-lane bridge. The Blackwell Ultra architecture literally doubles the throughput of those specialized SFUs, specifically for the exponential calculations that were causing the whole bottleneck in the first place. And here it is. This is the payoff. Just look at this new pipeline. The first step's the same, but notice how that softmax phase is now just a fraction of the size it was before. By making the SFUs twice as fast, that horrible idle time for the tensor cores has been almost completely wiped out. The traffic jam is gone, the whole operation just flows. Okay, so that's the theory, right? But what does this actually mean in the real world? Let's look at the numbers and see the actual measurable impact of this change. So the engineers cooked up this special test, a synthetic benchmark, designed to do one thing and one thing only: hammer that specific exponential calculation over and over again.
And the results, as you can see, are just night and day. The Blackwell Ultra is about 2 times faster than the standard chip. They built a 2-lane bridge, and it is officially moving twice the traffic.
All right, a 2 by gain on one tiny little instruction is cool, but what does that really mean for a big AI model? It means this, a roughly 35% increase in overall throughput. To put that in perspective, every single time the model generates a word or a token, it's now doing it 35% faster. In the world of large-scale AI, where every millisecond is money, a 35% gain from one targeted fix it's just huge. And here's where it gets really interesting. The speed up is actually most noticeable when you're using less precise math, like FP8. And you might think, wait, why would that be? Well, using that low precision math is like taking the speed limit off the Tensor Core superhighway. All the cars are going at maximum speed. This means they get to the SFU bridge even faster, which causes an even bigger traffic jam. So when you fix that bridge, you're not just clearing a normal jam, you're clearing a high-speed pileup, and that unlocks massive gains.
Okay, so let's zoom out. What does this one very specific, very clever technological fix tell us about the broader future of making AI faster?
This quote from the source material really just nails it. The race to build faster AI isn't just about making the superhighways bigger and faster anymore. It's about making sure the entire system is balanced and that all those smaller, specialized roads can actually keep pace. And you have to remember, this SFU fix isn't some one-off magic trick. It's just one piece of a much, much bigger strategy. NVIDIA's attacking this problem from every single angle, optimizing how memory is handled, how data moves around, how the software itself talks to the hardware. The big takeaway here is that they are systematically hunting down and eliminating every potential traffic jam in the system, no matter how small it seems. So the really crucial takeaway is this. The whole game of AI speed has changed. It's not a game of brute force anymore. It's a delicate balancing act. Because as soon as we make one part of the system way faster, a new, previously invisible bottleneck is always going to pop up somewhere else. Which kind of leaves us with one final thought. What's the next one? Hiding in plain sight.